In our everyday lives, striving for efficiency and maximum value plays an important role in everything that happens around us. Whether it be from our devices and gadgets, to our everyday appliances, and to our everyday decisions, efficiency and the maximum value is a factor in attaining the best performance. How is it possible, though, to calculate and determine an efficient maximum value in what we do? This is where the concept of maximum flow comes into play. Maximum flow is a concept that is under the topic of graph theory. In summary, it is the highest amount of flow of any material being moved within a network from the source to its destination. When answering a maximum flow problem, we are particularly interested in the question, how much flow can be pushed through the network without exceeding the capacity of an edge? Now you may be asking, what do we mean without exceeding the capacity of an edge? When looking for the maximum flow of something, a flow graph will be used. A flow graph has multiple nodes, wherein it begins at the source node. The source node is where the flow of the material will originate and start at. The flow will then pass through the edges. In a flow graph, the edges have their own corresponding flow value and maximum capacity. Now, it is important to know that the flow value must be less than or equal to the maximum capacity of the edge. If the flow value were to exceed the capacity, then the graph would automatically be wrong and the maximum flow would not be found. Finally, the corresponding flow will go to the sink node. Essentially, the maximum flow is a bottleneck value for the amount of traffic the network can value from the source to the sink node. The flow graph and maximum value can be seen in many different situations, and the flow graph can represent these situations. A few examples can be that the edges are roads with cars, wherein the maximum flow would represent the number of cars the road could sustain in traffic, or underground piping with water, wherein the maximum flow would represent the volume of water that is flowing within the pipes, or even wires with electrical currents passing through, wherein the maximum flow would represent the net electric current that the system can sustain. If the flow value were to exceed the maximum capacity, it would be the same as an overflowing pipe that has started to break or leak, or too many cars stuck in heavy traffic for hours, or a wire that has been filled with too much electric current and is starting to overheat or fry itself. Now, how can we determine the perfect amount of flow to input in a flow graph? This is where we introduce Fulkerson and his algorithm. His algorithm is one of the algorithms used to find the maximum flow of a network. The method repeatedly finds augmenting paths through the residual graphs and augments the flow until no more augmenting paths are found. To have a clearer idea of what a residual graph is and what augmenting paths are, let's look at an example. The term augmenting paths means that it is a path of edges within the residual graph, such as these two examples. When looking for augmenting paths, it is important to look for the bottleneck value or residual capacity in the flow, which is the edge with the smallest capacity within an augmented path. The residual capacity will be the number to determine the amount of flow to input for the created augmented path. For example, the augmented path SABT, the edge AB has a capacity of 5, which is lesser than the other edges within the path, meaning that edge AB is the edge with the residual capacity. In the next augmented path, it is observed that the edge D to A has a capacity of 3, which is the least one out of the other edges, making it the residual capacity of 3. Now let's start off from the beginning from what we learned so far. We start off with the augmented path of SABT having a residual capacity of 5. We input a value of 5 into the path. Next, we follow the next augmented path we found earlier, SDACT, having a residual capacity of 3. We then input a value of 3 to all the edges of the path, giving the sink value a total of 8 so far. Although it seems we used both sides from the source, we could still use the same edges to make another augmented path. This is also known as augmenting the flow of paths we made, allowing for more flow to pass through the graph and go to the sink. By using the augmented path of SDCBT, we are able to squeeze in a little bit more flow into the sink and input a flow value of 1. This increases the edge SD by 1 and the other edges, giving the sink value of 9 in total. Looking at the graph now, does this mean that the algorithm process is finished? No. The algorithm also introduces the concept of reverse edges or cancellation or backwards edges. This essentially enables us to go to the opposite direction of the edge. Let's take a look at the graph. We can see that we can make an augmented path of SADCT. This is only possible because the edge A to D can be used as a backward edge. There are also certain rules in making a backward edge. The edge's capacity cannot be 0, and if it were to go backwards, it cannot lead back to the source. Now let us input a value of 1. We then subtract 1 from the backward or residual edge due to it becoming backwards. We then add 1 more flow to the other edges in the augmented path and add 1 to the sink. After careful observation, there are no more available augmented paths that can be made, and the maximum flow value is 10. The time complexity of solving a maximum flow problem is big O multiplied by E and F, wherein E is equal to the number of edges and F is equal to the maximum flow. Now that we have learned the basic concepts and procedure of the flow graph and Fulkerson's algorithm, let us see if we can solve a real-life situation. Let's take a look at this example. Rafael Rivera has just taken up one of his father's poultry and truck businesses, and he needs to determine the max capacity of delivery trucks he can take on the road. He is currently stationed in Magalang, Pampanga, and he needs to transfer farm and gravel materials to Porac, Pampanga. The roads and highways are usually clumped with traffic, and there are even imposed truck bans in certain areas at certain times. Below is the graph of the routes the trucks can pass through, but Rafael is trying to get the most maximum value in an efficient way from his station to his destination. Now let us take a look at the graph and implement what we have learned. Find a path, find the bottleneck capacity, and then augment. The first path we can choose is SADT. We can see that the bottleneck capacity is 5, meaning that we will input 5 to the edges and to the sink. Now let's look for another path. We can make an augmented path of S, C, D, and T. This path also has a bottleneck capacity of 5, meaning that we will input 5 to the edges and to the sink. Now let's try to input a backwards edge into an augmented path like we have learned before. I have noticed that the edge A and D is in the middle and is at full capacity. I have the chance to turn it backward and use it as a backwards edge. The path that will be made will be S, C, D, A, B, and T. The bottleneck capacity of this path is 3, due to the capacity of 5/8 in C and D. We add 3 to the other edges, but we subtract 3 in the edge of D and A. The sink then receives another value of 3. Now let's look for another path. Another one can be S, A, D, B, and T. Since the flow value of D and A has been lowered, we can use the path again. The bottleneck capacity is 3 due to A and B being 2/5, and we then add 3 to the sink. For careful observation, the flow graph does not have any more possible augmented paths, and the maximum flow is 16. To answer Rafael Rivera's dilemma, according to the flow graph, he should decide moving his trucks in the following routes of S, A, D, and T, S, C, D, and T, S, C, D, A, B, T, and S, A, D, B, T to get the maximum output possible. And just like that, we are able to solve a business-related situation to get the highest output in an efficient way. As said before, maximum value and efficiency plays an important role in many decisions and what we do in everyday life. Although in reality it may just be a bunch of graphs, it is important to have a clear understanding of such topics in order to approve and attain the best results in what we do.